The quest to decipher the mystery of motions has been a central narrative in the tale of human discovery. From the philosophical debates of ancient Greece to the rigorous experiments of the scientific revolution, this journey charts the evolution of our understanding of the forces that govern our universe. Throughout the journey, we will dive into the fascinating world of Newton's laws of motion.
In 4th BCE, Aristotle was held as an authority to motion laws. He saw that an object needs a force to keep it moving. A rolling ball always needs to come to a stop and otherwise needs energy to keep it moving. Aristotle was later proved wrong by Galileo, who saw that a force is not required to keep an object moving. He argued that the ball stops because it is acted upon by friction between it and the surface. If there is no friction, the ball will continue to move forward. It was a world where people adhered to the qualitative observation of Aristotle, describing motion without the benefit of quantitative measurements. In Aristotle's vision, a universe of order and hierarchy, motion was a tale of contrasts, natural and unnatural, earthly and celestial. Though later proved inaccurate, his theories framed the intellectual discourse for centuries. As Europe awakened in the Renaissance, so did scientific inquiry. The unquestioned acceptance of ancient authorities began to waver, setting the scene for groundbreaking discoveries.
A legendary story begins with an apple falling from a tree and striking Isaac Newton on the head. This seemingly unusual event sparked the curiosity of one of history's greatest scientific minds. But what happened next? Newton's curiosity didn't end with the apple incident. It marked the beginning of a scientific journey during which he conducted a series of groundbreaking mathematical experiments with objects. These experiments accounted for various factors, including friction, air resistance, mass, length, and time, all playing crucial roles in formulating his laws of motion. With the historical background in mind, let's delve into the heart of Newton's profound discoveries. He observed, experimented, and calculated tirelessly, ultimately leading to the formulation of the three laws of motion. Newton's first law, often called the law of inertia, states that an object at rest will remain at rest, and an object in motion will stay in motion unless acted upon by an external force. His second law, expressed through a mathematical equation, relates the force applied to an object to its mass and acceleration. This groundbreaking formula laid the foundation for modern physics. Newton's third law, perhaps one of the most intuitive, asserts that for every action there is an equal and opposite reaction. This law serves as the cornerstone for understanding interactions between objects in motion.
On a starlit July night in 1969, humanity witnessed one of its greatest technological triumphs. Apollo 11, a spacecraft born from the dreams of a generation and the laws of Sir Isaac Newton, embarked on an unprecedented journey to the moon. As millions watched with bated breath, Neil Armstrong became the first mankind to walk on the moon, traverse the vastness of space, a voyage meticulously planned and executed in harmony with Newton's laws of motion. When Neil Armstrong set foot on the moon, he said the famous words,
"That's one small step for man, one giant leap for mankind."
Every burn of the rocket engines, each adjustment in trajectory, and the delicate dance of lunar landing were guided by the invisible yet unyielding principles set forth by Newton centuries before.
The manufacturing of spacecraft, once a dream of science fiction, has become a reality thanks to Newton's laws. These laws explain how objects move in space, allowing engineers to design and construct spacecraft that can travel vast distances, explore other celestial bodies, and unlock the secrets of the universe. Consider the construction of space stations, such as the International Space Station. Newton's laws govern the behavior of objects in orbit, ensuring that the International Space Station remains in a stable orbit around the Earth. This remarkable achievement wouldn't be possible without our understanding of these laws. The launch of rockets into space is a testament to the precision and accuracy afforded by Newton's laws. Every rocket launch involves complex calculations based on these principles, so it can ensure that there's an appropriate amount of fuel to reach their intended destinations. Newton's laws continue to guide space exploration missions to distant planets and celestial bodies. Space probes like the Voyager missions, the Mars rovers, and the New Horizons spacecraft rely on these laws to navigate through the vast expanse of space and collect valuable data about our solar system. Beyond our own solar system, astronomers use the laws of motion to study distant galaxies, stars, and cosmic phenomena. Newton's laws help astronomers understand the movement of celestial bodies, the dynamics of galaxies, and the forces that shape the universe.
As we near the conclusion of our journey, let's take a moment to reflect on the profound impact of Newton's laws on the world of science and engineering. Imagine a world where Newton's laws were never discovered. Our understanding of the universe would be vastly different, and our technological advancements would be limited. Newton's legacy continues to shape the world of physics and engineering, inspiring generations of scientists to explore the mysteries of the cosmos and drive our quest for knowledge forward. Thank you for joining us on this captivating journey through the realm of Newton's laws of motion. The story of motion is a continuing legendary journey of human curiosity and intellectual bravery. As we stand on the shoulders of these giants, we look forward to the next chapter in our unending quest to understand the